There we go. So today let's talk about reusing security solutions. The way we're going to do that, we're going to start off with some motivations and context around why I'm suggesting that you should do that. And then we'll spend the majority of time in this talk looking at some case studies about how we've reused security solutions at Meta in domains outside of security. We'll then move on to some limitations and talk about why this isn't always going to work. And finally, I'll send you off with some conclusions. Very briefly about me, my name is Bleaney. I'm a security engineer at Meta, the artist formerly known as Facebook. And I work mostly on Python security topics. The motivation in the context of this talk really starts with kind of how we do security at Meta. So our goal is to build generalized solutions that let us shift left and solve problems at scale. That sounds kind of high level and wishy-washy, so I'm going to go into each of those pieces a little bit more. When I talk about solving or building generalized solutions, I'm thinking about things like bug bounty programs or static analyzers, things that have the ability to not just find the current bug that we know about now, but also have the ability to adapt to the next bug that comes out. So bug bounty programs are a good example where, as the security industry is evolving and new research is happening and things like that, people outside can find that research and look for bugs and report it to you, and you can discover a new class of bug that maybe nobody at your company even knew about. When I talk about this concept of shifting left, I'm talking about this sort of continuum here, the continuum of bug badness, you can think about it. And on the leftmost side of the continuum, it's prevention, right? Our best case scenario for a bug is it just can't ever exist. You have frameworks or something that makes it so that the bug doesn't happen. Next best case scenario is tooling finds it automatically. Maybe the tooling finds it while you're writing code or when you put it up for review or before it ships out to production. Our next best case after that is finding it manually. Finding bugs manually, it's good, you're catching bugs, but it's not a thing that scales. There's hundreds of millions of lines of code at Facebook, and it's just really hard to have someone review every single one of those lines of code and every change that happens. Finding a bug externally through bug bounty programs like I mentioned is good, we can find it, we can fix it, but ideally we'd never get to that situation. And the last two scenarios there of never finding a bug or having that bug be exploited are obviously really undesirable. When I talk about the whole concept of scale, I brought up that we have hundreds of millions of lines of code at Meta. And so we've been investing in tooling for a long time to try and move more and more bugs into the automatically found category. And at this point, we're at about, in 2021, half of all the bugs that we found were found by tooling, the other half being through our more human-focused review methods. That's all the context that takes us to a point in 2019 that a lot of people in this room are probably familiar with. We discovered that we had been logging a bunch of passwords, hundreds of millions of passwords in plain text. This wasn't something, it wasn't like we deliberately took a password and decided to store it in the database. This is, think like a crash dump or something where you grab, there's plain text passwords in memory, things like that. But regardless, that doesn't matter to users. It's passwords stored in plain text, and that's a problem. And that was found once in a security review, but we knew that this pattern could appear elsewhere. And so that's where this concept of generalized toolings came in. We didn't have a tool that was designed to look for passwords being logged at that point, but we had tools that could look for data flows. And so we went and used our tools that were designed for detecting SQL injection and things like that via data flow, and turned around and used them to try and detect passwords being logged. And that's where, to me at least, this whole concept of reusing security tools in new domains comes from. That brings me to this thesis that we can and we should be applying security solutions to new problems outside of the traditional space of your OWASP top 10 security vulnerabilities, injection attacks, things like that. Now we're going to move into some case studies. I'm going to go really deep on one case study and then give you a brief overview of a number of other case studies just so you know that this isn't a one-off situation. Our first case study here is the Instagram Threads app. For those who aren't familiar with it, it actually was just recently shut down, but the purpose of this app was, among other things, to sort of help you connect with your close friends. And one of the things that it did is it would let you provide an automatically generated status that your friends could see. So it would tell your friends things like, I'm on the go, my battery's low, I'm at the library, whatever it is. And some of those statuses obviously require your location. And we need your location to calculate that status, but there's no reason we need to hold on to it after we've calculated the status. So what I wanted to do was make sure that we didn't hold on to that location data. And so this case study is about a security review I did. This isn't the story of a bug that was found. This is the story of a security review and tooling that we set up to try and ensure that we didn't still hold on to that data. The generalized problem that I wanted to solve here, going back to this concept of good security tools will solve generalized problems, was I wanted to track data flows and make sure that that data didn't end up where it shouldn't end up. To do that, I use something called static taint flow analysis. Starts with the concept of tainted data. This is data that originates from or after transformations is still somehow influenced by a source of data that we want to keep track of. That taint source is just something that we get to define. We get to say where it originates. And the place where it ends up is called the taint sink. If you put that all together, you get the concept of static taint flow analysis. We're tracking this tainted data from source to sink. It can start off and it can look really simple, right? You can have one function that returns a source of data, another function that is a sink, and you just pass the data, and it's a simple call graph like that. The call graph can get longer. You can have more sources. You can have more sinks. Or sorry, you have further away sources, further away sinks. You can have a point where you've got your call graph and your sources and your sinks are 10, 20 function calls away from each other. And just to make it more complex, you can have multiple sources, multiple sinks. So it can get really complicated, but at its core, static taint flow analysis is just about tracking data from a source to a sink. We built this to catch traditional security vulnerabilities, right? A SQL injection attack where you have user-controlled data that enters the application. It gets passed around, it gets put into this SQL query, and it gets executed. So that's the kind of thing it was designed to catch. But we can also use it to catch things like location data that is passed around the application and ends up in a logger or something like that. Again, this is contrived code. This isn't a bug that was found, but this is the detections that we were able to set up to make sure that this bug never got written. We have a number of tools that we use to do that. Zonkolon for hack code, Pisa for Python code, and Mariana Trench for Java code, more specifically Android apps usually. The latter two, Pisa and Mariana Trench, are actually open source. So anyone who is sort of sold on some of the ideas I talk about in this talk, you can go and download those and start testing them out right now. You can also take this concept of static taint flow analysis even further. My coworker Ibrahim was talking about this at Black Hat last year about the cross-repo taint exchange concept, where you can actually join taint flow analyzers together. So you can say, in the example of threads, you can follow in the Android app from the GPS API to an HTTP request. And that taint flow is all in Java code. And then when you hit the backend server that's written in Python, you can track from the sort of API layer down into a service call. And then you can, again, hop through the taint exchange and start analyzing a backend service that's written in Hack or some other language. So you can make static taint flow analysis even more powerful by joining analyzers across languages. Now, this static taint flow analysis has been probably the most successful use case of applying security tools in other domains at Meta, and I could make a whole talk about that, but I think I would bore you. So I'm going to briefly give a couple more examples, and then we'll move on to other case studies. Obviously, the one I introduced at the beginning of this talk, logging of passwords. This, the solution we were using to search for this happening elsewhere was repurposing our static taint flow analysis tools to look for password logging. We also use these tools to look for private data being returned to users. So data that a user shouldn't be able to see, we want to detect and know if it ever does make its way back to an exit point on our applications. And we've even gone further afield with this. So when we have performance regressions, we know that a performance regression happens because a certain conditional statement changed and a new code path was hit or something like that. And what we've used is we've used the static taint flow analysis to attribute what caused the conditional statement to change. So we can attribute that back to our experimentation frameworks and say this experiment was flipped. Somebody flipped this bit, and that was what caused the performance regression. And then we can more easily undo that in order to fix whatever the bug was. Now for our next couple of case studies, I'm going to go through them a little bit more quickly, a little bit less depth, but I'm just going to show you some of the breadth of other security solutions you can reuse. It's time to talk about another mistake that Facebook made. So again, people in this room may have heard about it. Hundreds of millions of users' data was scraped. And that was a really terrible thing to happen. It wasn't a hack, but to users it doesn't matter. Their data got out there anyways. And what we really wanted to do was, we wanted to be able to prevent this from happening, and if it ever does happen, know about it as early as possible and get it taken down. That means we have a generalized problem here where we want to incentivize people who spot these issues to let us know about them so we can get them fixed prior to exploitation or as soon as possible post-exploitation. If you're thinking back to what I was saying at the beginning of the talk, it might sound familiar to the bug bounty program concept I was describing, right? It's a time-tested solution in the security space to say, like, hey, if you find a SQL injection on Facebook, we'll pay you, tens of thousands of dollars, whatever, if you tell us about it and we fix it. We can also reuse this concept on the data abuse side. So we set up a data abuse bounty program where if you find scraped data sitting out there somewhere, we'll pay you to tell us about it so we can find out about it and get it taken down. And if you find a way to scrape a lot of data, we'll also pay you to tell us about that so we can fix it and so that no one ever ends up abusing that endpoint. Another use case is a sort of different approach, a defense-in-depth approach to password logging. So it's going to come up a couple times throughout this talk. The defense in depth is really important, not just in security, but in lots of other domains. And one of the layers of defense in depth we can add to prevent password logging is make sure that systems that don't need to have access to a plain text password never have access to a plain text password. The generalized problem here that we want to do is just we want to obfuscate this information in transit. And for anyone on the security side, again, this is a really familiar concept, right? Encryption's been used in a bunch of different ways. You've had HTTPS, you've been browsing over HTTPS for years now. And so you can do that on the password logging side too. So you're not probably going to be able to see the text of that, but that's a screenshot of a request of me logging into Facebook the other day. And there's no password field anymore. There's this giant blob of encrypted data instead. And that way, any intermediate server, the web server that's processing this request and sending it to the backend server that handles password hashing, it doesn't need to have access to that password in plain text. And so if something goes wrong again and there's a crash dump or whatever else and it gets logged, we're not logging it in plain text. Obviously, logging it encrypted is still not perfect, but it's better than plain text. Our final case study here is about unsafe data access. So briefly, to understand this case study, you need to understand the way we do data access at Meta is we have a layer on top of the database where all data access goes through, and it's sort of a privacy layer that bakes in all the rules about what users are allowed to see what data. So one example here of where that layer might come into effect is if I block you. So if I block you, that layer is going to say anytime the website is processing a request for me, I can't see data about you. I can't see your profile picture, your name, your messages, anything. And in my experience, like, you're just not there. But what happens if I want to unblock you? I need to be able to see your name and your profile picture in order to say, like, yes, this is the person I want to unblock. And so there are really limited scenarios where you need to sort of bypass this like default on restriction to what data can be loaded on behalf of a user. The generalized problem that sort of maps back to, or one of them, is ensuring that developers understand the risks of an API like this, and they use it sparingly, and they don't misuse it, and they don't misunderstand what it's for. In the security side, if anyone who's used React before might have come across this dangerously set inner HTML attribute in React. And for those who aren't too familiar with HTML, the inner HTML is a cross-site scripting vector. So it's useful and it exists in applications for limited purposes, but it's also a way that you can introduce cross-site scripting into your application. And so the solution with React there was they renamed it to make developers really, really aware that this API that is inherently risky has problems, and it's dangerous. And so a reviewer or the author is aware when they're looking at this code that like, oh hey, I need to really scrutinize this piece. We can do the same thing, or we do the same thing, I should say, on the privacy side. So when you need to use the API that bypasses these privacy checks, it's going to tell you, it's going to be big and scary and say this will bypass privacy checks. This is another time where I need to talk about defense in depth. This is not the only way that Meta prevents people from bypassing privacy checks. This is just one of many layers that we add in to make sure that when developers do use an API like this that exists, that it is done sparingly and they're very aware of what's going on there. Now we need to talk about some limitations though. I've given you a couple case studies where we've sort of reused different kinds of security solutions and they've been relatively successful, but not every time that's going to be the case. The first thing is just thinking about the solution or the tool that you're trying to repurpose. Sometimes tools aren't general purpose. Sometimes they're built for a very specific use case and they're just not going to translate well. And so you need to be thinking about what solutions do you have that are general purpose, that solve a generalized problem and not something too niche. The next thing is organizational design. A lot of security teams are set up in such a way that they have a team of experts that staff a queue that can sort through a bunch of alerts, right? There are a bunch of false positives and then there's some true positives. And the danger or the cost or the value of those true positives make it worthwhile to sort through all the false positives. But if your organization is set up such that you don't have that kind of team, that queue, or you don't have the will to set it up, then trying to repurpose a security tool that gives a lot of false positives is not going to work out. You're just going to upset developers or upset whoever's looking at those alerts, and it's never going to be put to use. And then, of course, we come back to the concept of defense in depth. So in security, we love the concept of defense in depth. You should have a bunch of layers of tools that are protecting you and never rely on one solution. Same thing comes when you're translating tooling, when you're translating security tooling to other domains. You shouldn't assume that any one tool that you translate is going to solve all your problems, and so you should translate the concept of defense in depth as well. You can use frameworks, static analysis, humans, bug bounty type programs. All these things can be layered together to try and make whatever solution whatever problem you're trying to solve more comprehensively covered. To conclude all this, I'm going to just briefly review the thesis of this talk, which was that we can and we should be applying security solutions to new problems outside of the traditional space of security. Hopefully you walk away realizing that great security solutions are solving generalized problems, and those generalized problems exist in plenty of domains that are outside of your traditional OWASP top 10 security problems. These solutions can help you out in performance problems, compliance problems, privacy, data abuse, and I'm sure many more that I haven't thought of, but maybe you can. And finally, it's important to remember that these solutions aren't always going to work. Don't try and fit a square peg into a round hole. So look for the times that you can have a relatively quick win from a tool and you don't need to spend months or years rewriting it to try and reapply it somewhere else. Thank you to all these people who helped make the talk possible in one way or another. If these problems sound interesting to you, these kind of tooling stuff sound interesting to you, feel free to talk to me some more. You can shoot me an email. I'll be on Slack and I'll be available for chatting after this. And with that, I'll open up to any questions.